Okay, this is lesson 27 of module 4. It's titled Nature of Solutions of a System of Linear Equations. So we're going to continue talking about systems of linear equations and what types of solutions they have. Also in this lesson, we have been finding solutions for these linear equations by graphing them and looking at the point of intersection. But now we're going to start solving these systems of linear equations algebraically because we can't always see it from a graph. So let's get started, and we're going to start by looking at the first three exercises that you have in your notes. And the directions say to determine the nature of the solution to each system of linear equations. So looking back to what you did in lesson 26, dealing with parallel lines, look at each of these sets of equations, 1, 2, and 3, and determine if they have a solution or what the nature of the solutions are. Okay, so go ahead and work on that and then come back and we will talk about it together. Okay, so let's look at number 1. And remember, when we're doing these, we are looking for slope because we discovered that if the slope of two lines is equal, then those lines are parallel, and they will never intersect. So there won't be a solution to an equation like that. So we need to find slope. So in this first set, we can find the slope of the second equation easily. The slope of the second equation is -3/4 because it's the coefficient of the x. But for the first equation, let's go ahead and put it in slope-intercept form. So I've got 3x plus 4y is equal to 5. So I'm going to subtract 3x from both sides, or add a -3x. So I get 4y is equal to -3x plus 5. And when I divide through by 4, I'm going to find, to get y by itself, I'm going to find that the slope of this equation, because this becomes a 1 here, the slope here is -3/4. And the y-intercept is 5/4 right here. So in set 1, this equation here has the same slope but a different y-intercept to this equation. Therefore, these lines are parallel and there is no solution. Okay, no solution to that one. Okay, so in the second equation, I want to determine if these two lines have the same slope, and neither of these are in slope-intercept form, but I can look at these and be pretty sure they're not going to have the same slope when I solve for y. But we'll go ahead and do it just to be sure. So I have 7x plus 2y is equal to -4. I'm going to do some steps in one step here. I'm going to skip a little bit. I'm subtracting 7x from both sides. So I've got -7x minus 4. And then when I divide through by 2, I'm going to get y equals -7 halves x minus 2. Divided everything by 2. So there's the slope and there's the y-intercept of that equation. The other one is x minus y equals 5. And so I'm going to get -y is equal to -x plus 5. And then if I multiply everything through by a -1 to get rid of that -1 in front of the y, I'm going to get y is equal to x minus 5. So the slope in this case is 1 right here. The coefficient of x is 1, so that's my slope. And the y-intercept is negative 5. So this has one solution, and it will be the point of intersection. So it's a unique solution. Okay, let's look at one more. And remember, you're supposed to have looked at these yourself. So if you haven't, go ahead and pause. Okay, so I'm going to take each of these equations. I've got 9x plus 6y is equal to 3. I'm going to subtract the 9x, so I'm just left with 6y equals negative 9x plus 3. Divide through by 6, and I'm going to get y is equal to negative 9 6x plus 3 divided by 6. Every term when I do this, when I divide by 6 on one side, every term, everything that's being added together here has to be divided by 6. So this equation becomes y, and I'm going to simplify these fractions here. Common factor of 3 and 3 right here. So this is going to be negative 3 over 2 times x plus 1/2. Okay, so that's the first equation. And I can see the slope, negative 3/2, and the y-intercept 1/2. Okay, so then I have 3x plus 2y is equal to 1. Subtracting the 3x, I get negative 2, or I'm sorry, 2y is equal to negative 3x plus 1. So y is equal to, and I'm dividing by 2, negative 3/2 x plus 1/2. Okay, so I took and divided every term by 2. 2 over 2 is now 1, negative 3 over 2, and 1 over 2. Okay, so what do we notice here? When I took these two equations, put them in slope-intercept form, I got the exact same equation. So I got a slope of negative 3/2 and a y-intercept of 1/2. And one thing I know is that if two lines go through the same point and have the same slope, they are the graph of the same line. So every point on these two lines will coincide, will be solutions to both equations. Okay, so looking back to 1 and 2, I can clearly see no solution in 1 because of parallel lines, one solution in exercise 2 because the lines have different slopes and different y-intercepts. But then in this one, how many solutions would I have in this case? And so that's something that we're going to talk about now. Okay, so we could start by finding some solutions for each of these. So I'm gonna clear my screen here. One thing you might notice about these two equations is that if I take this equation, I notice that all I have to do is multiply every term by 3, really what I'm doing when I'm doing this is multiplying both sides by 3, isn't it? So I think that's a little more clear. So 3 times 3x is 9x, 3 times 2y is 6y, and 3 times 1 is 3. And so by multiplying both sides by the same number, I got that first equation here. And so let's see if we can find some solutions to the equation, the first equation, 9x plus 6y equals 3. So let's do an xy table. And let's put in 0 for x. And what then would I get for y? So I would have 9 times 0 would be 0, so this would drop out. So I'd get 6 times y equals 3. So it would have to be 1/2, right? Kind of makes sense. That would be my y-intercept. And what if I make y equal to 0? So if I put in 0 for y, then I have 9 times something equals 3. So that would have to be 1/3. So x is 1/3 when y is 0. Okay, so both of these are solutions to the first equation. So what I want to do is check them in the second equation. So let's check this point first, the 0, 1/2. So I would have 3 times 0 plus 2 times 1/2, and I'm checking to make sure that's equal to 1. So I get 2 times 1/2 is 1 equals 1. So that solution checks out. So let's check the next one. Let's give myself a little room here. So for the next one, I would have 3 times, this time x is 1/3 and y is 0. 3 times 1/3 plus 2 times 0. And I'm asking myself, is that equal to 1? And again, I can see that it is. 3 times 1/3 is 1, plus 2 times 0 is 0, plus 0 is equal to 1. Okay, so what have we shown? We've shown that we have at least 2 solutions to the first equation that work in the second. And you're probably maybe saying to yourself by now, there's infinitely many solutions because these 2 equations are going to graph as the same line. They have the same slope, the same y-intercept. They are the same. They are the graph of the same line. And so this is a third possibility. So we could have no solution, we could have one solution, and we can have infinitely many solutions. Infinitely many solutions. So when we talk about the solutions to a linear system, we now know that there are 3 possibilities. The system can have one solution, and that happens when the lines have different slopes and therefore they intersect. They're not parallel lines. And so there can be one solution. There can be no solutions. And this happens when we have 2 distinct parallel lines. Different y-intercepts, but parallel. And then that will result in no solution. Or the third possibility now that we've looked at is that we can have infinitely many solutions. So these are graphs of 2 lines that have different, they look different, but it turns out that they are the graph of the same line. And we saw that in an earlier lesson where we learned that if the ratios, let's look at it. Okay, so I've got it recorded down here for you. So I've put our variables x and y in purple just to show that they're different from the ABC. The ABCs are constants. They're numbers that define a certain linear equation. But the x and y are variables. So we're going to let x be any number and we'll get a specific y. So if we have a situation where we've got 2 equations and we've got the a, b, and c here, a prime, b prime, c prime here. So these look like 2 separate equations. But we said that if these ratios of a prime to a is equal to b prime to b is equal to c prime over c, then we have a situation where these two are the same line. And that's what we saw was when we could just multiply one line, one equation by a number on both sides and obtain the next one. And that's exactly what we saw in this situation. 9 divided by 3 is 3, 6 divided by 2 is 3, 3 divided by 1 is 3. And so all I had to do was multiply this second equation by 3 to get this first equation. So they're the same equation, and this is true of that system. So there are infinitely many solutions when the equation's graph is the same line. Okay, looking at this first example 1, and this is an example that you don't have in your notes, but we're going to do a few. Don't worry about taking notes on these, because in the exercises that you do have, we'll do examples of all of these techniques. If you'd like to take notes, you're more than welcome if it helps you. Okay, so in this example, we have a system of equations right here. We can tell by the brackets. Y equals 3x plus 5, y equals 8x plus 3. We can see by looking at, because these are in slope-intercept form, because I have y by itself on the left-hand side, and then I can see the slope and the y-intercept here. So we know that there's a unique solution. There is one solution to this equation, and it's at the intersection of the two lines where they intersect. The coordinates of that point will be solutions to both of these equations at the same time. So these are simultaneous equations. Remember why we called them that. So if we look at this, though, it's not exactly on a grid line, but we could estimate what we think the solution is. So I would say that the x-coordinate is around 1/3. It's less than half, obviously, about 1/3. And the y-coordinate looks to be about 6 right here. So it appears that the solution to this equation would be about 1/3 6. Okay, so we could make a more precise graph, but there's a better way. And so for the rest of this lesson, and really the rest of this module, we're going to be talking about how to solve these linear systems using algebra and not using a graph. Okay, so we're going to use algebra. So first I want to give you a little example. We're going to talk about something that I think you'll be able to see it's true, and then we'll come back and use that to solve the system algebraically. Okay, so I'm going to use shapes instead of variables here. So if I know that triangle is equal to square in some way, and then I know that square is equal to circle, then what do I know about triangle and circle? Well, you could say, therefore, if those things are true, then triangle would have to be equal to circle, right? Because they're both equal to the same thing. And I could flip this around. If triangle is equal to square, I can say square is equal to triangle, and square is equal to circle. So triangle is equal to circle. Okay? So if I know this, then I know that. Okay, so think about that for a minute and let that sink in. And if you agree, let's go back to that example and I'll show you how we're going to use this idea and some algebra to find a solution to that system. Okay, so let's go back. So in this example, I know that y is equal to 3x plus 5 and y is equal to 8x plus 3. So I know something here. Let me get a good color here. So I know these are both equal to y, so I know that 3x plus 5 has to equal 8x plus 3. Because both of those expressions are y. And in my simultaneous equations, y in my solution is going to have the same value. The y coordinate of both of those equations will be the same in my solution. Okay? So if I set these two expressions equal to each other, then I'll know that I have the x coordinate of my solution right there, which is what I'm going for. So let's solve this. So I can start by getting the x terms on one side. Now notice I only have one variable now, which is nice, right? That was the thing that's tricky, is having those two variables. Okay, so after this first step, 3x minus 3x is 0. So on the left-hand side, I just have 5. And then over on the right-hand side, I have 5 is equal to 8x minus 3x is 8 minus 3 times x, or 5x plus 3. Okay, I'm trying to get x by itself, so let's subtract 3 from both sides. And I'm going to get 2 is equal to 5x. So I'm getting closer. Still want x by itself, so I'm going to divide by 5. And this is going to leave me with, I know I'm down here toward the bottom here, but it's going to leave me with x on this side is equal to 2/5. Okay, so what is that telling me? Well, that's telling me that's going to be the x coordinate, 2/5 of this solution, which is the intersection of these lines. So 2/5, our guess was 1/3. Our guess was 1/3. Well, 2/5 is pretty close to 1/3, because 1/3 would be 2/6. So 2/5 is pretty close. So that was a good guesstimate, but you could see by if we had gone with 1/3, we would have been wrong. So x is 2/5. So let's look at what I can do with that. Okay, so I've got x equals 2/5, and now I need to know what the y coordinate is. So we could put this in either of these equations. So let's choose the first one. So y is equal to 3 times 2/5 plus 5. Okay, so now we just straighten that out. Y is equal to 6/5 plus 5. 6/5 is 1 1/5. So y is equal to 5 1/5. I'm not 5 1/5, sorry. Let's get rid of that. It's equal to 6 1/5. Okay, so how does that go with our estimate on our graph? So we get 6 1/5 for y, and up here we had 6. Okay, so pretty close. All right, so let's just for fun, let's check and see if we use the second equation, what we would get for y. But let me record it. Y is 6 1/5. And let's go back. This time we're going to use the second equation. So we're going to say y is equal to 8 times 2/5 plus 3. So y is equal to 16/5 plus 3. 16/5 is equal to 3 1/5 plus 3. So here again, y is equal to 6 1/5. Okay, that's pretty cool, isn't it? So we can use algebra to find the exact solution to a system of equations. So here, again, here is our estimate from the graph, 1/3 and 6. Here is the actual solution, 2/5 and 6 1/5. So the coordinates of that point are 2/5, and I'm going to change that into an improper fraction. So this would be 31/5 for the y coordinate. Okay, and that would be the exact solution right here, the coordinates of that point. Okay, let's look at example 2 now, and again, you don't have this one in your notes either. Okay, so example 2 says, does this system of equations have a solution? And here's our system. Y equals 7x minus 2, and 2y minus 4x equals 10. So whenever I have a system of equations, to save myself some work, I should ask myself the question in the beginning, does it have a solution? And so I want to look and see if these two have the same slope. And I'm pretty sure they don't. This first equation is in slope-intercept form. Let's transform the second equation. So I'm going to get 2y, and I'm going to add 4x to both sides. So I'm going to get 2y equals 4x plus 10, positive 4x plus 10. And then dividing through by 2, I'm going to get y equals 2x plus 5. Okay, so these two equations are equivalent, and I can see that this system is going to have a solution. Yes, it's going to have one solution. Okay, but what is that solution? Okay, so I know it has a solution, so let's talk about what would that solution be. Okay, so we are going to find the solution to this system of equations without graphing it. And we're going to do it by a little bit different method than what we used in example 1. But I know that y is equal to 7x minus 2, right? And so what I'm going to do here is I'm going to rewrite this second equation. This is 2 times y minus 4x equals 10. Okay, and I wrote this big space for y here because I'm going to put something else in that spot. Okay, since I'm looking for the place where these two equations have the same solution, I'm going to substitute this expression, 7x minus 2, for y, because the two are equal, right? 7x minus 2 is equal to y. So I can put it in here. This is 7x minus 2. Okay, I don't like this 2 out here. It looks like a z. Hopefully that didn't confuse anybody. Okay, so this right here is just this equation, the second equation, with 7x minus 2 substituted for y. So now all I have is x, and I can solve for x. And when I do solve for x, it's going to be the x coordinate of our solution to the system of equations. Okay, so let's just simplify out this expression. I need to use the distributive property here. So I'm going to do 2 times 7x and 2 times 2. So I'm going to get 14x minus 4 minus 4x is equal to 10. Okay, so I've got, I'm going to make everything addition. So subtracting 4 is the same as adding negative 4. And subtracting 4x is the same as adding negative 4x. So I want to combine my 14x and my negative 4x. I can put those together because they both have x as the variable part. So this is going to be 10x. Let's go back to purple here. It's going to be 10x. 14 minus 4 is 10. 10 times x plus a negative 4 is equal to 10. Okay, so to get rid of that negative 4, I'm going to add a 4, and I get 10x is equal to 14. So x is equal to 14 tenths. And I could also write that as 7/5 if I wanted to simplify it. So 7/5 is the x coordinate of the solution to this system of equations. So let's get some room here. And what we want to do now is find the y coordinate. So we're going to find the y coordinate by substituting it into either of these equations. Okay, so I've got y is equal to 7x minus 2. So if I want to know what the y coordinate that goes with 7x as an x coordinate is, I'm going to put in 7/5 for x. So 7 times 7/5 minus 2. So y is equal to 49/5. And I'm going to put minus, let's write 2 in fifths, would be 10/5, right? Minus 10/5. So y is equal to 39/5. Okay, so 7/5 and 39/5. Okay, but just to make sure, let's put our x coordinate in to the second equation here. So I would have 2y minus 4 times 7/5 equals 10. So 2y minus 28/5 is equal to 10. And then I would add 28/5 to both sides, and I would get 2y is equal to, this is plus 28/5 also. 10/5 is 50/5, so this would be 50 plus 28, or 78/5. And that's 2y, so I need to multiply by 1/2. Multiply by 1/2. And I get y is equal to, and notice that 78 has a factor of 2, so half of 78 is 39, and this gives me 39/5 as well. So I know that 7/5, 39/5 is a solution to both of these equations, and that's what it means to be a solution to the system of equations. So this is going to be the point of intersection of those two graphs. Okay, so we're going to do one more example before we go on to the exercises that you have in your notes. So again, here's a system of equations, and the question I always want to ask myself first is, does this system have a solution? And so again, I need to look at the slope. I can easily tell the slope of the second equation is 11. The slope of the first equation, notice if I divide through by 4, I'm going to get y is equal to 26 fourths times x plus 4 over 4, which is 1. So that's an equivalent equation. So I can see that I don't have equal slopes. Therefore, these lines are going to have to intersect because they're not parallel. All right, so we can begin to work on it then. Okay, so we're going to solve this one by substitution, like we did in example 2. So I know that y is equal to 11x minus 1. This equation says these two expressions are equal, y and 11x minus 1. So if they're equivalent, then I can substitute one for the other. So I'm going to do that here. 4 times y is equal to 26x plus 4. Okay, and so that's just this equation. I'm going to put something in here for y. So the expression that I want to put in here for y is what y is equal to in this second equation, because I know I want to find the place where they have the same, they have a point that is a solution to both equations. So that's why I want to put this expression up here in this equation. And that will give me, when I solve for x, that will give me the x coordinate of my solution. And I'll be halfway done. Okay, so let's look at this. We've got 44x minus 4, because I had to multiply both terms there, is equal to 26x plus 4. Okay, so I'm going to start by subtracting the 26x. And when I do that, I get 44 minus 26 is, what is it? It's 18? Yeah, it's 18x. 14, yeah. 18x minus 4 is equal to, now this is minus 26x, so that becomes 0, and all I'm left with is 4 on this side. Okay, so to finish this off, if I add 4 to both sides, I'll get 18x is equal to 4 plus 4, which is 8. So if 18x equals 8, then x is equal to 8 over 18, dividing through by 18, which is the same as 4/9. It's nice to simplify, but it's not necessary. So there's 4/9. So x is 4/9, and that is the x coordinate of my solution to that system. So now I can go back and substitute it into one of the equations to find the y value. So I get, I'm going to use the second equation here. I get y is equal to 11 times my x value, which is 4/9, minus 1. So y is equal to 44/9 minus 9/9. I just changed 1 into ninths. And so y is equal to 35 ninths. Okay, and you could check it. If I put it into the other equation, I would get the exact same thing. So y is equal to 35 ninths. And so that is the solution to this system of equations. Okay, and I have a graph of this equation. And so our solution was 4 ninths, which is about a half, and 35 ninths, which is about 4, because 4 times 9 is 36. So it's about at 1/2 4. So if you look at this this system, here is the intersection of these two graphs. There's the equations of the graphs right there. Here's the intersection, and notice the x-coordinate is between 0 and 1, and it's about 1/2, and the y-coordinate is right about 4. So there is our system, and we can confirm our solution if we're not sure if we did the math right. If we graph those two equations, we can confirm our solution by seeing if it makes sense with the graph. And on this case, we can see that our answer is correct because it looks like the lines intersect at 4 ninths, 35 ninths, or about 1/2 4. Okay, so now it's time to look at our exercises. So let's look at exercise 4, and you do have this in your notes. Here's a system of equations, and again, we want to determine the nature of the solution to each system. So does it have one, none, or infinitely many solutions? If the system has a solution, find it algebraically, and then verify that your solution is correct by graphing. So for each one of these, we're going to find the solution algebraically and then graph to make sure that that it is right. Okay. Okay, so if you haven't already determined the nature of the solution to this system in number 4, yeah, you should pause the video and work on it. But I'm going to go ahead and talk about this one. Okay, so what I notice when I look at these equations is that if I take the second one, which is x plus y equals -7, and I multiply both sides by 3, I get 3x plus 3y is equal to -21. And this equation here is identical to the other equation. So not only do these lines have the same slope, but they are the same, they graph as the same line. So the nature of this set of equations, this system of equations, is that it has infinitely many solutions, because every solution on the first equation is also a solution of the second equation, because they are the same line. Okay, which means they're made up of all the same points. Okay, so we don't need to do anything further with number 4 because there's not a unique solution to find. So let's go on to number 5. Okay, so number 5 is this system. Y equals 3/2 x minus 1, and 3y equals x plus 2. So I want to first make sure that they're not the same line or that they're not parallel lines. And so I'm going to take this second equation here, 3y equals x plus 2, divide through by 3, so I could put it in slope-intercept form, or you could think of multiplying by 1/3, because this is going to be y equals 1/3 x plus 2/3. Okay, so clearly this equation has a different slope from the first one, so they're not parallel lines, and they're definitely not the same line. So there will be a unique solution to this system, and I want to find it by using algebra. Okay, so once again, I'm trying to find the point that is a solution to both of these equations. So I'm going to take this. I know that y is equal to 3/2 x minus 1. So I know that this expression is the same as this expression. And so I'm going to substitute it. So I'm going to take 3 times y is equal to x plus 2. And I'm going to substitute, instead of y, I'm going to put in 3/2 x minus 1. Because they are the same thing. They have the same value. They're equal to one another. All right, so using the distributive property, I'm going to get 9/2 x minus 3 times 1, is equal to x plus 2. So now I want to add 3 to both sides, and I'll get 9/2 x. Adding 3 gets rid of it on the left-hand side and makes this x plus 5. 2 plus 3 is 5. Now I want to subtract x from both sides, so I'm going to get 9/2 x minus, and I'm going to rewrite 1 as 2/2, and that's equal to 5. So 9 minus 2 is 7/2 times x is equal to 5. And then if I multiply by the reciprocal, I get x is equal to 10/7. All right, so let's remind ourselves what that 10/7 is. It's the x-coordinate of the solution to that system of equations. X equals 10/7. And so what I want to do now is put that in one of the equations, and I'm going to put it in the first one. Y equals 3/2 times x, and I'm going to put in 10/7 for x minus 1. So y is equal to 30/14 minus 1, which is 14/14. So y is equal to 30 minus 14, which is 16, over 14. And I'll go ahead and simplify that, and it becomes 8/7. So remember, that is the y-coordinate of our system of equations. 10/7, 8/7 is going to be a solution to both of our equations here. Okay, I want to show you a slightly different way of doing this same problem. Okay, so here's our system again, and let's look at how we could do this pretty much the same way, but maybe a little bit different way of thinking about it. So what I want to start by doing is multiplying the first equation by 3. I'm going to multiply both sides of that equation by 3. 3 halves x minus 1. So I get 3y is equal to 9 halves x minus 3. So I've got 3y is equal to 9 halves x minus 3, and 3y is equal to x plus 2. So because 3y, I have two different equations that both say 3y equals something. So again, because 3y is the same, it kind of goes back to that block and triangle and circle thing. Then I know that x plus 2 has to equal 9 halves x minus 3. So I can write that. I can say x plus 2 equals 9 halves x minus 3. Or the other way around, which we won't go any further because what I just want to do is go back and show you that that is exactly the equation we had at this step. 9 halves x minus 3 is equal to x plus 2. Just flipped around. Okay, so we might have gotten there a little bit quicker by doing that. All right, now we want to take this solution here and see if it is actually the intersection of these two lines. So we need to graph these lines, and we're going to be checking 10 sevenths, 8 sevenths. Okay, so I've put, I have a coordinate grid here, and I'll go ahead and number these. And we're going to graph both of these lines. Okay, so y equals 3 halves x minus 1. We know how to graph this. We can graph it by starting with the y-intercept, which should be right here at -1. There's -2. And counting off using our slope to find another point. So the change in x is 2. A change in y is 3. There's our next point right there. And so we wanted to draw a line through those 2 points. And so we'll see if we can do that. So it would be that line right there. And so now I need to graph our next line here. 3y is equal to x plus 2. And we put this one in slope-intercept form as well. And we got y is equal to 1/3 x plus 2/3. So when I graph that one, I'm going to graph using slope-intercept form again. The y-intercept is at 2/3. So we can mark that right there. And the slope is 1/3. So that means I go over 3 and up 1. So I'm going to go over 1, 2, 3. Go over 3 from my point and up 1. Okay, and that puts my point about right here, and I can draw the line between them. And so that ends up about right there. Okay, so what I want to double check is to make sure that my solution makes sense. So remember, my solution is it was 10 sevenths for the x-coordinate and 8 sevenths for the y-coordinate. So my intersection here, I'm going to mark in a different color, is right, oops, that's not where it is. It's right about there. And when I look at this, I can see that the x coordinate is 10/7 would be 1 3/7, which is close to 1.5. And it looks like it is, actually. And then 8/7 is just 1 1/7. So it's a little bit above the 1. And so our rough graph here verifies that this is the solution to this equation. Okay, let's look at number 6 now. 6 is written kind of a little bit backwards from what we're used to. We have x equals 12y minus 4, and x equals 9y plus 7. So these aren't in slope-intercept form, but we can tell that these are definitely not the same equation. In other words, they're not multiples of one another. And they're not, so they would appear to have a different slope. I could put these in slope-intercept form, but I really don't need to for what we're going to do, at least not yet. So, okay, so let's look at how would we solve this system of equations algebraically. We're going to do it by graphing, remember, but let's solve it algebraically first. So I know that x is equal to both of these expressions, right? So remember we had this, box equals circle and box equals triangle, then I know that circle equals triangle. So that's what's going on here. If I think of x kind of being equal to the box, so I have x equals this stuff and x equals this stuff. So therefore, those two things must equal each other. So that would look like 12y minus 4 is equal to 9y plus 7. Okay? So this idea here is the same as what I did over here. Okay, so now I'm going to be solving for the y-coordinate of our solution because this equation is all in y. So let's subtract 9y from both sides. And I end up with 12 minus 9 is 3y minus 4 is equal to 7. So 3y is equal to, adding 4 to both sides, I get 11. And y is equal to 11 thirds. So we just solved for the y-coordinate of that system of equations. And y equals 11 thirds. All right, so let's go ahead and put that in one of our equations here. And I get x, we'll use the second one, x equals 9 times y. My y is 11 thirds plus 7. Okay, so x is equal to 99 thirds plus 7. I could have simplified that before, but we'll do it now. So this is actually 99 divided by 3 is just 33 plus 7. I could have also simplified it up here first. 9 is 3 times 3, so a factor of 3 cancels. So anyway, however you get there, x is 40. So the x-coordinate of our solution is 40. And we could have, once again, we could have put 11/3 here to see what x would be. 11/3 here, this would end up being 44 minus 4, which is 40. So I would get the same thing either way. So that's my solution. So we should be able to put this on a graph and verify our solution. So let's go back and look at our two graphs and our two equations up here and make an XY table for them so we can graph them. Okay, so to graph these, I decided to just find two solutions to both of these equations and graph it that way rather than putting them in slope-intercept form. So for this first equation here, x equals 9y plus 7, if I let y equals 0, then x equals 7. And if I let y equal 1, then x equals 16. Okay, so there's 2 points for that equation. And then for this second one here, if I let y equals 0, x is -4. And if y equals 1, then 12 times 1 is 12, minus 4 is 12 minus 4 is 8. Okay, so let's look at what these graphs will look like here. I've got x is 7, y is 0 right there, and x is 16, y is 1. So the line would be something like that. Okay, so let's graph the second two pairs of points here. I've got when x is -4, so that's -5. So when x is -4, y is 0. So that would be right around there. Let's get it in a little bit. Okay. And then when x is 8, y is 1. So let's go up to 8 and 1 right here. And we can do a rough graph here. Okay, so here's something similar to what you might have gotten. And remember, the solution to this set of equations was the point 40, 11 thirds. So it'd be 3 2/3 on the y coordinate and 40 on the x coordinate. So let's look at our system. These have slopes that are very similar, and so when we come here right around 40, you could notice it's in the area of where the intersection is, and the y coordinate of that intersection is between 2 and 4, actually between 3 and 4. So 11 thirds is 3 2/3. I'll get my pen here. 3 2/3 and 40. So the y coordinate seems to check out, the x coordinate partially. This one was a tricky one to get accurate on the graph, and drawing it a little more closely would give us a closer approximation. But we can see that the graph is checking out with the solution roughly that we solve for algebraically. Okay. Okay, our last exercise is kind of an open-ended one. There's many solutions to this exercise. It's just write a system of equations with 4, -5 as its solution. And so that's just something you're going to play around with. And I'll give you an example of one. I could have y is equal to x minus 9 and x plus y is equal to -1. Written as a system, 4, -5 is a solution to both of those equations. And so that is a system of equations with 4, -5 as a solution. So you should come up with something different. And we did one like that in a previous exercise. Okay, so let's just quickly summarize. This is a nice set of notes that you have with your problem set. And we talked about today that there were 3 possibilities for a solution of a system of linear equations. It can have a unique solution, which is another way of saying one solution. And it could have no solutions, and that's when the lines are parallel and never intersect. The slope of the 2 equations is the same. Or it could have infinitely many solutions, and this is the case where the 2 equations are actually equations for the same line. They just look different. And so this details out what I just said here. And so we talked about the substitution method, and this is where we had equations that look something like that. And remember we said, you know, if box is equal to circle and box is also equal to triangle, then I know that triangle equals circle. And that's where we can, since these are both equal to y, we can set them equal to each other and solve for x, and then use that to get the y coordinate as well. Okay, another thing we could do that shows up in this example here is I don't have, you know, x equal to something and x equal to something, but if I multiply the second equation by 3, then I get 3x equals 3y plus 15, and then I can set those 2 parts equal because I have 3x equaling some expression, 3x equaling some expression over here. So I know that those 2 expressions have to be equal. Okay, that's kind of messy, but that's what it's saying right here. Okay, so this set of notes is kind of nice because we've seen a couple different things we can do to solve a system of linear equations algebraically. And in the next couple lessons, we'll see even more methods for that. Okay, so good luck with the problem set on this. I think you'll do fine.